In this video we'll go on to number 29 since we didn't have an opportunity to finish it in the last video. 29, we have f of x is equal to 4 over x squared plus 1, and I would definitely rewrite that as 4 times x squared plus 1 to the negative first power. Now f prime of x then would be negative 4. We have a chain rule here. X squared plus 1, we leave the inside alone, subtract 1 from the exponent, multiply by the derivative of the inside, and then we simplify and get negative 8x x squared plus 1 to the negative second. When we can rewrite this as negative 8x over x squared plus 1 to the second, and either choose to do this as a quotient rule or as a product rule. And I think I'm going to leave it as a product rule, and we'll just start that over on the side. So the second derivative would be 1 negative 8x d2. So we have a chain rule here. Outside function is x to the negative second. We bring down the negative 2. X squared plus 1. We reduce the exponent by 1 and multiply by the derivative of the inside function. So that's 1 d2 plus 2, which would be x squared plus 1 to the negative second d1, which is negative 8. Alright, simplifying, we have 2 times 2 is 4 times 8, which is 32, and negative times negative, so we're going to get positive 32x squared times x squared plus 1 to the negative third power minus 8 times x squared plus 1 to the negative second power. We want to factor out the least common multiple, which would be x squared plus 1 to the negative third power, and that will leave us 32x squared, then minus 8 times x squared plus 1, and negative 3 plus 1 equals negative 2. So we can simplify again, and we would get 32x squared minus 8x squared minus 8, or x squared plus 1 to the negative third times 24x squared minus 8. From this we can factor out an 8, and we get x squared plus 1 to the negative third times 3x squared minus 1. Now that can be written as 3x squared minus 1 over x squared plus 1 to the third power. Now it may be possible to factor, but we're not going to get too much out of that process. Instead we want to solve. Now a rational function is 0 when its numerator is 0. It does not exist when its denominator is 0. In this case the denominator will always be greater than 0, so there's no problem with that. So this is equal to 0 when 3x squared minus 1 equals 0, 3x squared equals 1, x squared. X squared is 1/3, and x would be plus or minus 1 over square root of 3, which is plus or minus root 3 over 3. Now, Square root of 2 is roughly 1.4. Square root of 3 is roughly 1.7. Root 3 then over 3 is roughly 0.6. And so we're ready to begin. We can make our number line, and we have potential points of inflection at negative root 3 over 3 and positive root 3 over 3. I have 0 as a test point, negative 1, positive 1, and we're working with the second derivative here. Alright, all we need to do is plug into the numerator. The denominator will always be positive. Negative 1 squared will get positive. Plug in 0, we'll get negative. Plug in 1, we get positive. And so we have concave up, concave down, concave up, and we have x equals plus or minus root 3 over 3 points of inflection. And we are concave up. For negative infinity to negative root 3 over 3, and from root 3 over 3 to infinity, concave down, from negative root 3 over 3 to root 3 over 3, and we'll bring in the graphing calculator and take a look at what this comes out to be. So we'll put in our function 4 divided by x squared plus 1. Remember to put the denominator in parentheses. We choose a window negative 5 to 5 for x and y, and we get a graph that looks like a bell curve. And we don't have much space, but we can see that at about negative 0.6, roughly here, the graph changes from being concave up to being concave down, and at roughly positive 0.6, it changes from being concave down to concave up. And so the graph confirms our analysis, and that'll be it for this video.